Hi guys, hope you're doing good. I'm Pavan Kumar Yeddanapudi. I head analytics and engineering automation team. That's my background. So in this video blog, we are actually going to go and see what are the different ways that you identify if the data is normally distributed or not. So why is this topic very special? So let me give you the background of it, and then we'll quickly go into the ways to identify if the data is normally distributed or not. So, in real time, the data follows a normal distribution if the data has been picked from a naturally occurred data. This is one of the statements of the central limit theorem. So if the data is naturally occurred and it is of large volumes, it is assumed that data follows the normal distribution. So, and because we deal with the real-time data these days and the volumes is very high, we assume the data follows the normal distribution, and most of the machine learning algorithms are built around this assumption. So take it linear regression, basic models also, right? I'm not going to into the advanced models, but yeah. So even the basic models go with an assumption that the data follows a normal distribution, and all the models has been built on that assumption. So we as a machine learning engineer or a data scientist, we have to make sure the input data that we are giving to the model, right, model building algorithm is first of all normally distributed, and then we expect the correct equation or the expected equation as an output. In case if you're not doing that, definitely your regression output is not useful for your problem solving, right? This is the reason why verifying if the data is normally distributed or not before you actually give the data to the machine learning algorithms or the models, this is one of the important checks. So what if the data doesn't follow normal distribution? Yeah, we have different methods like transformation techniques. We actually transform the data unless the transformed data follows a normal distribution, and then we run the regression models on that, and then use the results and de-transform it for the output. Yeah, these are all the techniques that we use. So yeah, because it is very important for us to identify if the data is normally distributed or not, I have picked up this topic and I wanted to show it programmatically in Python. How do we really achieve this question mark, right? So how do we identify and what are the different methods? That is going to be my topic of discussion going forward now. So one of the very important characteristics of normal distribution is what you're seeing on the screen. This is a very ideal case where your normal distributions mean, median, mode are exactly the same. That is one of the primary characteristics of the normal distribution. So if any data distribution mean, median value is the same, yeah, so that data is normal distribution. That's what that's what one of the properties of the normal distribution is. It is also called as Gaussian distribution. That's fine, right? Now, yeah, we will also see, as you see on the screen, consider this, the dotted line in the center is a mean, median, mode of a normal distribution. The another characteristics of normal distribution is the data is symmetric on either sides from the mean value, right? So what are the two characteristics? I mean, now that you know, a normal distribution mean, median, mode value will be 0. And the normal distribution, we will almost have the symmetric data set on the left, on the right hand side of the mean value, right? This is the second characteristics. And the third characteristics is this, the bell curve, right? So more intense the bell is, the intensity of the bell will tell you how mode is higher for the mean value, right? So you can have the same symmetricity over the mean value. For example, if you take 10 data points, each of the data point as 10 value, right? You will have mode as 10, right? You will have mean as also 10, but it doesn't mean that it is having a bell curve. It is a single straight line, that's it. If you have a straight line, the mean value will always be, wherever might be the mean value, you will always have symmetricity on the left and right hand side. But if there is a bell shape in the data, that is when we call that data as a normally distributed. This is the basics. So I'm just spending 5 minutes on the basics so that you understand why are we doing it. And then anyway, I'm going to show what are the different ways to identify if the data follows a normal distribution, because visually doing it every time is not, accepted, or not a good way to identify, because you have to do everything programmatically. So yeah, we will do it programmatically, not just visuals. But visuals are good for learning the basics, so that's why we are spending time. So as we just discussed, we need a mathematical metric, one single value, right, that will help me to identify if the data is symmetric over the mean on the left and right, and how intense is my bell curve. If I have these two values, I can definitely tell if my data is normally distributed or not. So let me take an example. So you see the data might not be exactly symmetric over the mean, right? On the, you can see the curves like this. You can also see the curves like this in real time. And you can also see the curves like this, which is called normal distribution, right? We call, right, this as, so consider, this is the mean value of this data, the third data set, that is normal distribution. We call those two mathematical metrics that will help me to identify if my data is symmetric or not over the mean, and how intense is my bell curve over the mean. If I'm able to find out these two values programmatically, which uses mathematics in the background, from the data, I'm good to comment or to conclude if the data follows a normal distribution or not. All right. So the first one is not normal distribution, because your mean, median, mode will never be the same. Second one is also not normal distribution, because your mean, median, mode are never equal, one of the characteristics, right? Now, but what is the first one called? What happens to the skewness? Okay, skewness is nothing. Skewness will tell you the symmetricity of the data, and kurtosis will help you to identify the intensity of the bell curve in the data. So as you can see in the curve number 1 and curve number 2, there is no symmetricity over the mean. So the skewness value will tell you if it is symmetric or not. But in the third value, the skewness is not there. It is exactly symmetric over the mean. So skewness will be 0. Right? The kurtosis for the 1 and 2 value, you will have a very less kurtosis value, right? Very higher kurtosis value, negatively or positively, depending on what type of kurtosis mathematical equation are you using. But I will make it very simple. Similarly, for curve number 3, if the kurtosis is 0, that means the data is following a normal distribution. Okay, so I'm not going into the mathematical equations, for skewness and also the kurtosis, but I'm going to, use the Fisher technique in the skewness, where if the skewness Fisher technique in kurtosis, if the kurtosis is 0, that means bell curve intensity is good enough to tell that it is following a normal distribution. Similarly, if skewness is close to 0, that means the data is symmetric over the mean. These are the two things. So coming back to these 3 bell curves, so this curve is called as positively skewed because it is not exactly symmetric over the mean. And the second one is called negatively skewed. And the third one is not skewed, or also called as normally distributed data. All right. So this is the background. You need to know these backgrounds, because I'm very much interested in building the foundation. All others will actually follow, right? So a normal distributed data can be identified if it is normally distributed or not by using 2 simple metrics. One is the skewness of the data, 2 kurtosis of the data. Skewness will tell you how symmetric is the data over the mean. Kurtosis will tell you what is the intensity of the bell curve over the mean. And anyway, you have the third characteristics which you can already measure, right? Mean, median, mode. If all of these 3 values are very close to each other, that is also another sign telling you that data is normally distributed. So the simplest one, mean, median, mode, I'm not discussing in this, but yeah, you can also try that. Okay, so let's see how let's see that in Python. What are the different ways now to identify if the data is normally distributed or not? And I'll quickly start with skewness and kurtosis itself, and I'll go to the another methods. I'm actually showing you 4 different methods in this blog, know how to identify a data is normally distributed or not. Let us quickly start with that. All right. So to save time, I have executed all of this. So I just loaded my libraries, and I have created two data sets. One, a randomly generated normal distribution data, and the two, randomly generated uniform distribution data. So the randomly generated normal distribution data will look like this, exactly very similar to what we have seen in the slide a few seconds back. And normal distribution data is just normal. It looks like a straight line passing through, y-axis. That's it. So this is my normal distribution data, right? So for all the methods that we are going to go through now, the result should actually tell you that the data set with the name non-data is a normally distributed data, and the data set with uni-data is not a normal distributed data. That is the expected output of all the methods, 4 different methods we are going to see now, right? So let us quickly start with Skew Test. So there is a method, there is a package or a function in this scipy.stats. Skew Test will basically tell you whether the data is symmetric over the mean or not with a null hypothesis. I'm definitely, one thing that I'm assuming is, before you actually go through the further steps of this blog, I'm assuming that you are aware of null hypothesis testing and p-values, statistics, all of these terminologies. If not, I recommend you to go back, refresh that and come back and check this session. You will definitely get it. Okay, this is my assumption, so I'm moving ahead with this assumption. So this Skew test will basically test with a null hypothesis that the data follows a normal distribution. So if you're by default the significance level is always the 5%, but anyway you can decide if it has to be more than that or less than that, right? Lesser is the significance level. That means you need a very strong evidence to prove that your hypothesis is correct. That's what I read as, right? So with the 5% of significance, that means if you have a p-value greater than 5%, definitely you are accepting the null hypothesis, or you fail to reject the null hypothesis. These both terminologies are the same, but to keep it simple in this video, I'll call it accepting null hypothesis. So when I run this Skew test on the normal data, the p-value is 73%, right? That is far greater than 5%. That means the Skew test will tell me that my data is symmetric over the mean. I'm accepting the null hypothesis that the data might be uniformly distributed or symmetrically distributed over the mean value. I think this is not data follows normal distribution. Data follows symmetric distribution. That is my null hypothesis for Skew test. All right, I'm correcting it here. All right. So that is my Skew. Now what would be my kurtosis? Okay, so before I go to kurtosis, I have a lot of tests here, so don't worry about that. So let me show you the Skew test of uniform data. For the uniform data also, the Skew test is 65%. That means it is greater than 5%, right? That means this also tells my uniform data is symmetric over the mean. This is the reason why I just said few minutes back that not just by skewness you can conclude if the data is normally distributed or not. Skewness will help you to identify if the data is uniformly distributed or symmetrically distributed over the mean, symmetrically distributed. And uniform data is also symmetrically distributed. That's the reason your Skew test is also valid for uniform data. But when it comes to kurtosis, see, the kurtosis of normal distribution is close to 0, right? This is close to 0. But the kurtosis of uniform data is not close to 0. It is far away from 0. So the closer the 0 value of kurtosis, because I'm using a Fisher is equals to true, Fisher is equals to true is nothing but it will subtract 3 from the kurtosis mathematical equations. So if it is close to 0, that means your data is intensely bell. Bell curve is very intensive. That's what it means. So if you don't like Skew test, if you don't want to decide basis on the p-value, there is another function called Skew. So if you just say Skew and the data that you pass, If the skew value is very close to 0, that means the data is symmetrically distributed over the mean. So that is the reason your skew output for normal data and the skew output for uniform data is also close to 0. So now the conclusion using kurtosis, first method, this is first method. Using skewness and kurtosis, if you want to test if the data is normally distributed or not, skewness should be 0 and kurtosis should also be 0. This is method number 1. And the second method is D and P test, right? Normally you will find the package name as normal test. This is the name of the package inside your Python, but it is called as D and P test. Internally it uses D and P technique to identify if the data is normally distributed or not. It is nothing different from skewness and kurtosis. D and P test will basically check the skewness for you and kurtosis for you. It will combine both of them and it will give you one consolidated output to decide whether it is normally distributed or not. That means it is making your life a bit easy. Instead of doing 2 to 3 steps to identify if data is normally distributed or not, D and P test will tell you in one single output whether the data is normally distributed or not. So if you just run normal test and give the data, so if you see the p-value, yeah, again this D and P test null hypothesis is nothing but it's a two-sided test. That means if it is 5%, anything less than 2.5% and anything greater than 97.5%, you reject the null hypothesis. So if you see here, it is close to 90%. That means you are accepting the null hypothesis. What is accepting the null hypothesis in D and P test is nothing but the data follows normal distribution. So your p-value for a normal test should be greater than 2.5% and less than 97.5%. And if you see the same thing for uniform data, your p-value is exactly 0. That means it is less than 2.5%. You reject the null hypothesis that the data is normally distributed. That means because you are rejecting, that means this particular data set is not following a normal distribution, right? This is method number 2. Method number 3 is Shapiro-Wilk test. So Shapiro-Wilk test will basically use again a different mathematical equations of the models to identify if the data is normally distributed or not. And this particular test assumes with the null hypothesis as the data follows normal distribution, and it's a one-sided test. So if you have a p-value greater than 5%, good enough. Your data follows a normal distribution according to that significance level, right? But there is one problem with Shapiro test. If your data size is more than 5,000, Shapiro test is not basically advisable to use. Instead, we go with method number 1, 2, or 4, which I'm going to discuss. 4 is next, Anderson method, right? All right. So similarly, if you take this data set and if your p-value is greater than 5%, yeah, you're done. You are close to, the highest is the p-value. Your model is very, very confident that the data is following a normal distribution curve. So what is the third method? Shapiro-Wilk test. And the output is a p-value that you have to read like this. And the same when you run for the uniform data, your p-value is 0. That clearly shows that you have to reject the null hypothesis here because it is less than 5%. So your null hypothesis is nothing but it follows a normal distribution. So definitely Shapiro will tell you whether the data is normally distributed or not if the p-value is greater than 5%. That was method number 3. Now method number 4 is Anderson test. All right. So it is also called as Anderson-Darling test, right? So Anderson-Darling test is also a it works a little different than your normal than your Shapiro-Wilk test or your DNP test, right? So how the Anderson it will give you everything that you have to do. It's a very simple comparison, right? So you give a data, you tell what distribution you want to actually verify. So Anderson test will actually work for multiple distributions, not just normal. It can also test geometric distribution, right? It can also test logarithmic distribution. So it has got it can test a lot of distributions of the data. That's why you need to tell what distribution you are trying to test using Anderson-Darling test. See the result of this Anderson-Darling test, very much interesting. So this is a statistics value. So statistics, I'm not going to go into that, whether it is Z value or T value or something like that. Let us be a layman. Let us create the thumb rules. What does Anderson-Wilk, Anderson-Darling test tells is, this is the array of critical values. These are the arrays of significance level. For what significance level, what are my critical values is here. By default, everybody refers to the significance level of 5%. So for the 5% of significance level, my critical value is 0.918. Okay. So what Anderson-Darling test tells is, if your statistics value, this value, is far greater than this value, then you are rejecting the null hypothesis. Again, Anderson-Darling test assumes the null hypothesis is nothing but your data follows normal distribution. If this statistics value is less than this value, critical value, that means you are accepting your null hypothesis that the data follows normal distribution. So given this background, just check the outcome. The statistics is 0.17, which is definitely less than 0.918. That means your data is following normal distribution. You are accepting the null hypothesis. Where on the other side, the statistics value for a uniform data is 123. That is very, very far from greater than 0.918. It is falling on the very right corner of this statistics value. That means you are rejecting the null hypothesis. Your data is not following a normal distribution. All right. So I have taken you through the 4 different methods. I have given you the background of why normal distribution is very important. The fundamental of identifying normal distribution is always skewness and kurtosis, and hypothesis tests will come later. And we have gone through the 4 different methods to identify it programmatically using Python in this blog. So that was the one. And I really wanted to conclude this, definitely these are not only the 4 methods. There are other methods like K and S test, which will help you to identify if the data is normally distributed or not. But from whatever I have seen so far, I have been, doing good with these 4 methods known to identify if the data is normally distributed or not so far. So I thought it is good to share with you guys, and you can adopt them if you are willing to. That was the intention of this blog. So yeah, there are some limitations for these also, right? For example, all the except the Shapiro-Wilk test, other tests cannot intake multi-dimensional data, but Shapiro-Wilk test can take multi-dimensional data and tell you whether the data is normally distributed or not. That's the power of you can tell the power and advantage of the Shapiro-Wilk test. But at the same time, it cannot it is not accurate if your data points are more than 5,000. That's another disadvantage of Shapiro-Wilk test, right? So yeah, that's it. So in case if you have any comments, please help me to improve. Please provide your suggestions. I'm very much happy to take your feedback, and that will help to improve myself as well. All right. So in case if you want to get in touch with me, these are my coordinates. You can get in touch with me. I'm active on LinkedIn, emails, yeah, and that's my contact number. If you want to ping me on WhatsApp, feel free to do it. And please like and subscribe this video if you like it. And yeah, please share the knowledge. I love to share the knowledge, and that's why I'm here. Thank you guys. See you in my next blog. Bye-bye.